Okay, hello, can you hear me? Let's wait for 2 minutes while others join. Okay. We have 12 people who have joined. I was hoping that we can start when 20 have joined. Okay, so I will start now. It's 10 minutes in, so others can join us afterwards. Okay, I think we have lecture 2, some material in lecture 2. All right, can you hear me and can you see my screen? Okay. All right, so yesterday we discussed phases, right? And we were able to look at the forms. As we said, phases are nothing but complex numbers. And we have seen how we can be able to present complex numbers in the Cartesian as well as the polar form. And we look at the arithmetic, addition, multiplication, division, and subtraction. We've talked about how phases or how electrical signals can be considered as sinusoidal waves that can be easily characterized using the phases as their own mode of characterization. We have looked at how we can be able to take a sine wave and convert it into phases by taking the amplitude and dividing it by √2 to get all the root RMS. And after that, we were able to also draw the Argand diagram, which is where you have, if you have any phasor, you can be able to draw a corresponding Argand diagram. After that, we were also able to look at some examples on how we can do these conversions and how we can be able to determine our phases. We also, yeah, I think that's what we have done throughout yesterday. So today we are going to complete this lecture. We're going to look at RLC circuits and AC analysis. Okay. So are we all on the same page? Good. So RLC circuits. R stands for resistor, L stands for inductor, and C stands for capacitor. Okay. This in AC circuits, these elements are the characteristics of a transmission line and also the loads that are associated with an AC. They all have what we call an impedance. Impedance is nothing but the opposition, okay? Opposition to current in the circuit. For the case of R, the type of opposition it provides to a current is purely real opposition, and the impedance of a resistor is given by XR, and that equals to R. However, for an inductor, the opposition XL is J omega L, where L is the value of that inductor. In the case of capacitor, XC is equals to 1 over J omega C, or you can write it as minus J omega C. Okay, if you multiply this 1 over J omega C, you multiply it by J and divide it by J, which means it's the same thing. So J and J, you have what? Minus, right? Minus 1. So minus 1 goes up, divided by what? Omega C. and that J is there multiplying it, so we get minus J omega C. So these are the corresponding impedances of R, L, and C. So whenever we are going to do analysis of an AC circuit, if I give you a value of a resistor, you can use it, you can plug it there, no issues. But if you are given values of a capacitor or inductor, then you should know that you need to get its impedance, and the impedance is going to be in what? It's going to be in complex form. So you need what? You need pacers to help you in that regard. Okay. Omega is a common term, you know it. Omega is 2 pi f. F is the frequency. In Nigeria, we are using 50 hertz. In America, they are using 60 hertz. All right. That clear?
Yes, sir.
Okay. So the question now is, how did we come about this equation? For example, in the case of an inductor, where did we get the J omega L? Why not just L, as in the case of resistor? Well, there is Faraday's law of the coil. Okay, if you have a coil, Faraday says that for that coil, the voltage across it is equals to ITR plus LdIdt. Okay, so if we say let the current in phasor form become I sine omega t, that means here we can be able to replace this with I sine omega t, and also we can do that here as well, which will give us what? Vt equals to Ri sine omega t plus L di sine omega t dt. So go back to your calculus. This here has no issues, but this one here, if we differentiate di sine omega t with respect to t, what do we have? Well, I is a constant, right? Therefore, I is going to go out. So it's going to go out and multiply itself by this L. So we will have Li. Okay? So we are left with what? D sine omega t dt. Okay? So chain rule, you can easily do this one. The omega is going to come out. Sine, d sine of t is going to be cos what? Omega t. Okay? So that means we have Li omega cos omega t. That's the differentiation of this one. Well, this I'm sure is very easy, and you guys can follow this. You can do this evaluation very easily. Are we together? So,
Yes, sir, we are together.
okay, so that's how we got this to this point. Okay. We can also do some trigonometric analysis, right? Cos omega t is nothing but sine omega t plus 90 degrees. Okay. So if we are now going to go back to phasors, okay, this now from sine, we want to go to Cartesian form. We can replace this as what? 1 plus j0. And this one can also be 0 plus j. Cos omega t, if you go back to complex form, this is the complex part, okay? It's just j. Sine omega t is just 1, for example. So here you are left with Ri, okay? This is 0, so no problem. For us, what? J omega Li, okay? So we are left with this. So in the coil, we have resistance. So we have this term, and then we have the j omega L here, okay, multiplied by I. And that's here, you can just say V is equals to XR plus XLI, okay? So if you already know XL as j omega L, and you remember this equation that R is R, no difference, XR is the same thing as R, then you know that the voltage, according to Faraday's law of coil, is nothing but XR plus what? XLI. That clear?
Yes, sir.
Some people are trying to join. Okay. So let's dive in. So let's look at a simple circuit, and we want to try to do some analysis here. Okay, and this analysis we're going to use something similar when we are analyzing a transformer. Okay, so try to understand how this is going to be done. So first of all, you have a 50 Hertz voltage of 220 volt RMS, and it's applied to a series combination of resistor and inductor. Resistor is 10 amps. The inductance is 38 millihenry. Okay. So the first question is, what is the RMS value of the current that is flowing in the circuit? And the second question is, what is the RMS voltage across R and L? So this V. So what's this voltage across this, and what is this I that is going around them? Okay. So here we have a series combination between the resistor and the inductor. So we know the impedance of R is simply 10 ohms, right? XR is equals to R. So it's 10 ohms. But what of XL? XL is nothing but what? J omega L. All right, what is omega? 2 pi. And what is L? 38 millihenry. So we are 0.038, right? And this will give you 12 ohms. Okay, so if we are combining them, we know XL. For example, XL is omega L. So the combination is the summation. Since they are in series, if you have resistors in series or impedances in series, what do? You sum them up, right? So the combined impedance Z is going to be R plus JXL. And R is 10 plus J, what is L, is what? XL is 12, okay? So this gives you the combination. Now that you know the total impedance and you know the V, you know, remember Ohm's law. If you know resistor in a circuit, you know, and you also know the voltage, you can find the current according to Ohm's law. Okay? So this is what we are saying. For this circuit, if you are to draw the phasor diagram, the R is in the horizontal x-axis, and then the XL is in the vertical axis, whereas the resultant is across the center. All right. So here, as I said, according to Ohm's law, since this is Z, so V equals to IR, right? So I times Z, and Z is equals to what we've just calculated. So what we are supposed to find is what? Current. We are supposed to find current. So that means if V equals to IR, so I is equals to what? V over R. And that's what we have here. So we can say I is equals to V over Z. What is the V? We were given V already by 220 volts RMS. If you were given the voltage, not in the RMS, maybe you are given peak-to-peak voltage, don't forget to divide it by √2. Okay, don't forget to divide it by √2. But since it's already in RMS, we already know the value, and we know the first angle is 0. And this one, we were able to compute it, right? So simply now we have this, we have to convert this to polar form so that we can easily do the division. So who can give me what is this value in polar form? So what did we say yesterday? If you have A, B, right? So what is X? X is what? Root of A squared plus B squared, right?
Plus B squared.
Yeah,
Yes.
and what is psi? Tan inverse of B
Of B
over A. Very good. So if you do this calculation, what do we find X to be and what do we find psi to be? If you use your calculator, please, I think X will be around 15.6 and psi will be minus 50.2 degrees. Okay. All right. So if we are doing phasor division, what do we do? So you have 220 angle 0 divided by 15.6 angle minus 50.2, right? Sorry, is it
Yes.
minus 50.2 or 50.2?
3.20.
It's 50.20, right?
50.2.
Okay. Okay, so in phasor, we said we just divide these two, right? And these two we subtract. So 220 divided by 15.6. Okay, angle 0 minus 50.2. So what's 220 divided by 15.6? That's 14.1, right? 14.1 angle minus 50.2 degrees. Clear?
Yes, sir. It's clear.
Yes, sir.
Okay, so who's trying to join?
Yeah.
Okay, Hassan is raising up his hand.
Yes, sir. I was confused when you put the minus earlier, but it's clear now.
Ah, okay, it's clear now. All right. Okay, so now that we know the current, okay, and we also got the solution. So the next question is asking us to find the voltage, okay? So, but before we go to that, let's look at something here. If you look at this, you will see that the reactive impedance, which is the J component, it has made our current to be lagging the voltage. And this is something that is a property of an inductor. So if you have an inductor in your circuit, the current, okay, is going to lag. So if you have, let's say, a circuit diagram like this, and let's say you are using oscilloscope, when you look at it from oscilloscope, you will see your voltage, let's say like this, and you maybe use another scope, or you plot it on the same scope to see the current. The current is not going to be starting from the same place with the voltage. It is going to start after the voltage has started, okay? And this is lagging, so the current is going to lag behind the voltage. This is one of the effects, and we don't want to have a circuit that has this lagging. Okay, sorry guys, give me 2 minutes, just 2 minutes. Let me pick a call.
No problem, sir.
All right, so that's one thing to keep in mind, okay? We don't want lagging, and the reason why we don't want lagging is because if you have your current lagging, you will have what we call the power factor, and it will be low. If you have a very low power factor, this is going to increase losses in your circuit or in your network. So maybe a small power that you are requiring in your house because you have elements in your house that consume a lot of power, you end up paying huge money to KEDCO if you are in Kano, or KAEDCO, or whatever the revenue collection is. Because of that, that's why you see heaters, right? At homes, they have coils, iron, they have coil, and because of that coil, you end up generating huge power loss. And you are using that power loss to be ironing your, because it is being dissipated as heat, okay? And that's what you use to iron your shirt. You are using that loss, the power that is being lost, to generate heat that you can use to press your shirt, your clothes, and what have you. So, and that's why if you maybe are trying to have a simple solar, it will not work if you are going to put a lot of heaters, right, and use iron. Then you will quickly consume the limited battery you have. And if you are using it on NEPA, then they are going to charge you a lot of money. So it's all because of that conductor, that inductor, which is the coil. And that lagging is the reason why we have that power loss. And the power loss is exhibited in the form of heat. Okay, is that clear? So ideally, we would like to have the current and the voltage to be in phase. So they start at the same time. That will give you ideal situation where you are not going to have power loss. But that's not possible in real life. But we try to see, if possible, the angle between them is 0 degrees. But it's not possible, but we try. Is that clear? So there is a simple mnemonic you can easily use to remember this. Is civil, civil engineering, so civil should not be difficult. Capacitive circuit makes the I to lead the V. Okay, so capacitive makes I leading V, whereas V will lead I in an inductive circuit, or in where you have the L, right? So in an inductive circuit. So with this, at least you should be able to have an understanding of how these two things work. Okay. Because capacitors store energy. Okay. Inductors, they release energy. Now let's go to the second part of the question. What is the RMS voltage across R and L? So what is the voltage across these two? What is the voltage across the resistor, and what the voltage across the inductor? Okay. So the total V here is equals to VR plus VL. This you should know since you are in level 3. Okay. That means if VR is RI and VL can be written as this, that means we can easily do the computation in phasor form, right? What's RI? R is 10, right? And what the other one? Okay. XL is, okay, so XL is 12, okay? So let's see. We know this 2 pi, and we know L is 0.038, and we did the math, and it gives us 12 pi, right? No, 12 ohms, sorry. 12 ohms J, okay? This is this part. Okay, J is 12, so and this part is what? 10. So what is the current here? We calculated the current in the previous slide, the IRMS as what? 14.1 angle minus 52.
0.1.
Yeah, okay. So the voltage across the resistor is nothing but that 10, which is the R value, times 14.1 angle 52. So in this case, it's just saying this times this, which is 141. And the angle is what? We are adding the angle of R, which is 0, plus the angle of this, which is minus 52. So we are still the same phase, okay? Now we are done with VR. We can also calculate VL. We know this part is 12 ohms, Okay, j. And now we can be able to also multiply it by I. Okay. So this is this one. You can see in phasor diagram, if this is a V, I is lagging behind, and that's minus j. You can convert this to Cartesian to draw the Argand diagram. That should be okay. Here you can assume the V is what, 150, 141. Okay. And then this one, you have to do it and trace and see what is going to be this value. Okay. Now moving to the inductor part. Inductor is J omega L. You multiply it by the I, which we just computed. So J is this part is J12. And we multiply it by the current IRMS, which we obtained. So here, if you do the multiplication, right? So what do we have? We end up with, because this one is angle 1, angle 90 degrees, right? This is 12 angle 90, sorry. It's 12 angle 90. Okay, they have already done the multiplication. 14 times 12. Okay, it's 169. So that's why you have this. But you can verify with your calculator, okay? But J12 is nothing but 12 angle 90 degrees, okay? And you multiply it by 14.1 angle minus 50.2. So you multiply these two together and you add these two together. So what do you have? Okay, so we are happy now. We got our value, which is 90 minus 50.2. That's 39.8, right? 12 times 14.1, that's 169. So we know VL and we know VR. So this is done, this is done. Okay, so what's the resultant? Okay, this is the resultant. So this is something to keep in mind. What? Okay. So somebody is raising hand. Hassan Umar. Who else? Yeah, only Hassan. I think he has been raising hand since. Okay, Abdullahi, you have a question?
Sir, please, this phasor diagram, can you come back?
Okay, Raji, what's your question? Is it the same? Okay, it was not a question. Okay, so now let's look at the phasor diagram. Okay. So VL is what? Is 169 angle 39.8. So what did we say yesterday? If you have polar form like this, you can convert it into Cartesian form. Okay? You can convert it into Cartesian form. Somebody is making noise. I'm trying to figure out who that person is. So, Abdullahi, what's the Cartesian form of this value? Let's do it together so that you understand. A is what? X sine what?
X cos theta.
Cos.
And what is B? X.
X sin theta.
Okay. So if X is 169, what is A?
It's 130.
130. Okay. And what's B?
108.1.
108.1. So if you want to draw this, okay, you will have something like this. This is the real, and this is the imaginary. Okay, J is here. Here you have the real. So for V, okay, V by default, you know the A value for B is 130 and the B value is what? 108. So you can easily draw it like, let's say this is 130 and this is 108, okay? We can trace like this and we draw the resultant. So assuming this is V. Okay, fine. And what is I? This is I, right? 14.1 minus what? Minus this. So let's make I also to be in polar form, in Cartesian form. So the A of I is what? 14.1 cos of minus 50.2 degrees. And you can do the B as well, 14.1 sine of minus 50.2 degrees. Okay. So you can do this and you can find the value. What do you have?
9.08.
9.08. Okay. Plus or minus.
9.0.
What is sine minus 52? It's minus, right?
Minus 10.8.
Minus 10.8J. Okay. So that means the X is 9.08. I can maybe assume it to be around here. Minus 10 is maybe around here. So if I do this, so this is I. Okay, I is going this direction and V is going this direction. As you can see, this is the angle that is between them. And if you twist this, maybe remove this like this, you will end up with something like what you saw here. So if this is V, I is lagging because it's starting a little bit late. And first angle is what tells you by how much degrees is it lagging V. So normally whenever you have your pesos, you can just convert them into Cartesian, try to draw them, and you will be able to see your respective pesos on the Cartesian plane. All right. It's not going to be easy for you to do it from polar form. You have to convert to Cartesian. Then it's going to be easy. Okay, I hope that answered your question. Okay, the I and R. So if we know, like, okay, now we have VR, which let's say, and then this one is VL, two of them. Okay, this is VR and this is VL. And you can also draw each one of them separately on a peso diagram. I think we should also do that. I don't know, should we move to the whiteboard? It will be a lot better to demonstrate that on whiteboard. But some of you cannot see it. Okay, this is what I will do. Let me add an empty slide. There's nothing on it. Okay. Okay. So let's write our VR, please. VR is 141 minus 50.2. Okay. and angle minus 50.2 degrees. And what is our VL? It's 169, angle 39.8, right?
Angle 39.8.
Positive. Okay. So converting VR in Cartesian form, okay, we are going to have what? 141 cos minus 52 minus 50.2 plus, somebody do it for us, and somebody do VL for us.
Where calculator this?
Do we have calculators with us? Let one person do the first one and the second person do the second one.
So, sir, for VL,
14.
for VL,
Okay, for VL,
129.8 for the
okay, plus
for
what?
the L part.
Plus J what?
One 108.17 1.18
1.08.
108.18.
Okay. All right. What of VR?
90.2
90.2 minus
minus 108.3.
0.3J. Okay. So let's draw the Cartesian, for example. Okay. So let's try to see if we can scale it. 10, 20, 30, 40, 50. Okay, this is too small. This is 100. This is 50. Okay. So let's just try like this, 75, 75. Okay. Here, 25, 50, 7,500. Can do it like this also. Okay, so let's go for VR. 90.2 in the X and in the Y minus 108, which is around this place. Okay, so this is my VR. I will use a different color. Okay, now let's draw also VL 129, which is around this, and 108, which is around this place. So like this. Okay, so this is VL and this is VR, and the resultant is going to be this. This is their sum. This is the resultant. So if you go around summing them up, you know, this, you have some issues, because the resultant is not going to be the summation of 90 plus 129, which is around 220, right? And then this part is going to be 108 plus, okay, 1 minus, so that's around 0. So that's around 220, okay? So let's see what is that going to give us. But this is how you draw the phasor diagram, okay? If you do this, you have your Argand diagram, and nobody will say it's wrong. You can actually flip it and put one of this. For example, if you take this to be in the x-axis, okay, then this one, as you can see, you can twist or tilt it. You can tilt your graph. That's why here, what you are seeing here is the tilted graph, okay? It's like they have tilted the graph. But yeah, and this one is what we are talking about as the resultant. So if you do the sum, you will see this will not give you this VRMS, for example. So, but if we go ahead and convert it in Cartesian form, you will see our 109 that we got earlier plus what we got here. 109, okay, 129 plus 90.2. If you add these two guys, you get 220. Okay. So that's why we do the Cartesian. So we have the 220. But in phasor form, if you add the values, which is 141 plus 169, this is not equals to 220. But if you do the conversion to Cartesian, you will be able to get the 220. Okay, so is that clear how you can draw the Argand diagram? The main thing is just convert it to Cartesian and then do some scaling accordingly and draw. Okay. That clear? Or is it still confusing? I think it's clear, right?
Yes.
All right. So this is another example. Assuming you have an ammeter, I1, A1, and another one, and you want to find the value, and I think we did this one, right? Okay, no. So let I1, we know we are given the values I1 equals to 3 sine omega t, and I2 equals to 4 cos omega t. You can easily tell this one if you look at your oscilloscope. You look at the amplitude of the sine wave or the cosine wave, and you will be able to know. So we know of this. So this is the peak to peak, and we can convert it to RMS. Sine omega t is nothing but what? Angle 0. Cos omega t is nothing but angle 90 degrees. Okay. So according to Kirchhoff, for example, you can say, why don't I add these two up, right? You can do it, and you can use trigonometry, right? You know trigonometry, sine A, sine B. You can do that. Let's look at it. Okay. Let's do the trig analysis. 3 sine omega t plus 4 cos omega t. We can say, and the summation is of course going to give us something in this regard, x sine omega t plus theta. Okay, so let's look at it. This part here is going to be x sine omega t cos omega t, right? Sine A, sine B. From trigonometry, sine A plus B, right? What is that? Is sine A cos B plus sine B cos A. I'm sure you guys know of this from mathematics. Sine B cos A, right? So maybe the question is, how did we go from here to here, right? So from here to here, how did we go from it? Well, it's simple, right? 3 sine omega t, 4 cos omega t. Cos omega t can be what? Sine omega t, right? Plus theta, for example. Can assume it to be like that. Same thing here, you can see, let's say sine omega t plus also another angle theta. They are all in the same. However, whatever it is the case, we know that when we sum two phasors, we are bound to get a new phasor or a new sine wave with an amplitude, and it will also have a phase angle. Okay, this is something we know that we are bound to get. That's why here We don't know what's going to be the magnitude of summing I1 and I2. That's why we assume it to be X. And we don't know what is going to be the sine or the phase angle when we do the summation. That's why we use that theta as our variable. So now that we have like an idea, this is what is going to be the form of the summation of these two, we can use trigonometric analysis to break down sine omega t plus theta, and that will give you this value here. So that, what does this say? This is telling you that that means x cos theta is equals to 3. Okay, if you compare it, okay, if you compare this and this, sine omega t, sine omega t. So that means 3 is equals to what? X cos theta. 3 equals to x cos theta. And let's compare the second part, this one and this one. Okay, so you cancel this, you cancel this. So that means 4 equals to what? X sine theta. So now that we've established this, we can come and, you know, say, okay, why don't I put x cos theta here, okay, in place of this, and also do the same for this one, for example, and then also invoke trigonometric analysis. Now you will end up with these squares. So x, if I said summation of these squares, x squared cos theta squared is equals to 3 squared plus 4 squared, right? Because we said these two are the same. And when you do this summation, this one will give you what? 25. This one, x squared is common. Cos squared theta plus what? Sine squared theta can be taken in bracket. And this summation we all know from trig is 1, right? This summation is 1. So that is left us with what? X squared equals to what? 25. And if you take the square root, x equals to 5. So we now know the amplitude. Okay, so since we know the amplitude, we can find the first angle from any of these two equations. We can say 5 cos theta equals to 3, which means theta is equals to cos inverse 3 over 5. And with this, we will be able to get the angle, which is what? It is 53 degrees. Are we together? Guys, is this clear? This is something you do in Fourier transform, right? It's very simple. You have two signals, all of them are sinusoid, and you want to add them. You can do it this way. Nobody will tell you why did you do it this way. Okay, but it's a long shot. It's a very, very long shot. If you use phasor form, in 2 steps you will be done. Okay, it's that simple. For example, we know 3 sine omega t was originally 3 over root 2 angle 0, and I2 is this one. So we can just convert them to Cartesian, add them up, and we will be just in 2 steps, we will get our resultant, which is just going to be what we just finished calculating earlier. So I know maybe you have very sound foundation in trigonometric analysis, but if you are given anything like this, I will advise you not to go and do the trigonometric approach, because that is going to take a lot of time. All right? Is that clear? We were supposed to cover this part last week. Okay, but the main key takeaway from here is you understand how to do and how to work with phasor, which I am happy. Some of you are able to do the conversion directly and instantly from Cartesian to polar. And you know how you can come up with the Argand diagram. Not only that, you know how you can take advantage of these complex numbers to do AC analysis, AC circuit analysis, which we just did an example of. And the last example we just did was to show you how efficient using phasors is when you are trying to do computations with phasors. Okay? when you are trying to deal with complex number analysis or sinusoidal signals, what is the most efficient way of doing the arithmetic? And of course, it is the phases instead of doing the trigonometric approach. Is that clear? Are we together? Okay, what's your question?
So, this step-by-step solution
Yeah.
that you just showed us. So I don't know if it is contained in any PDF that we can go over.
It is
later.
in the lesson note. It's in the lesson note. The
Alright,
one
the
I shared with you
step-by-step
yesterday. Yeah, all this is there.
Alright, sir.
Go through it. It's there.
Alright,
Everything is there, okay? And if it's not, let me know, but it is. Okay. So we have 30 minutes. We are going to move to the next lecture, which was supposed to be the lecture of today. But yeah, we took a lot of time to understand phases. So any question on phases? Is it very clear to all of us? Anybody is not going to be scared when we are going to use complex numbers in our subsequent lessons. If you have any question, you still have some doubts, you don't know how to work with phases, I think it is high time you sit down at home over the weekend and practice. Muhammad, what's your question? Muhammad Al-Amin, you are raising your hand. What's your question? No question. Okay, this brings us to the end of our lecture 2. We can take advantage of this time that we have left to start looking at lecture 3. We can finish the first section, and then next week we can do the second section. Okay?
Sir, I have a question
Okay, what's your question?
about that graph that you draw on phasor diagram.
Yeah.
I have a
What's the
question.
question?
The number that you got 25, 50, 70, and 100. That is the question. One question about that.
25, 50, 70, and 100. Okay. 1 second. Where did we get 25, 50, 70, and 100? You should have stopped me right there so that I can respond to you immediately. Now I am even thinking, where do we have 25, 50, 60, and 100?
I think he's referring.
Oh, okay. You mean the graph?
The graph.
Yeah. No, it's just a scaling, right? I'm just trying to come up with something with a scale, to make sure that I'm not going to, you don't know how to do scaling, how to draw a graph. I think normally they teach you how to draw graph from secondary school, right? So when you have, so when you have a graph, it's up to you to decide what each square represents in scale term, right? You can assume the square to be 10, it can be 20, it can be 50. It's up to you. So because I don't have a graph sheet, that's why I am just drawing it by hand, assuming that the squares are 25 in size. Okay? Is that clear?
Okay. Yes, sir.
Yeah, it's just a graph. I'm not coming with the numbers from somewhere. Maybe if I have the graph sheet, it will have been a lot better. Okay?
Yes, sir. I understand, yes, sir.
All right. Okay, so let's move to transformers. Okay, let me share my screen. In the first class, or maybe the second class, lecture 1 then, okay, we talked about transformers very quickly. So we're going to now move into that in a more detailed way. The target is by the time we finish with transformers, you should be able to understand the mechanisms of a transformer, okay? You should be able to even design a transformer. That's the main target. In fact, I was speaking with Dr. Buhari, And he told me one of the projects that the students always do is to go and construct a transformer. And I think it might be a project that we also have to do in the course. If time will permit us and we finish transformer as soon as possible, that will serve as the project which I mentioned during our second class. Okay? So we will see.
All right.
So that's the main idea, for you to understand the mechanisms, how a transformer works, what it is all about, what the science behind a transformer. For today's lesson, the objectives are simply to understand the background, historical development, how did transformers come all about, understand how the operations of an ideal transformer works. Okay, I'm going to look at ideal transformer. You're also going to see some types of transformers. You will also understand how a transformer is constructed. We will do some power flow analysis of an ideal transformer. Not only that, we will apply impedance transformation concepts to see how we can do analysis of the ideal transformer. And lastly, we do perform circuit analysis involving ideal transformer. So the lecture is divided into two sections. The first one is just an overview. And then the second part, we're going to deep dive into ideal transformers. All right. So I'm not going to waste time with the history, but I expect you to go and read it. It's a very interesting history. Okay. In fact, I don't know, maybe I will be sharing some links for you, maybe for those who like documentaries. There is a very nice YouTube video, I think 20 minutes, that has explained how the rivalry between Edison and Tesla rooted, and how, you know Edison, right? Thomas Edison. You also know Nikola Tesla. Also,
Nikola Tesla. Yes, sir.
yeah. So these are the people that are behind transformers. Okay, Edison was the first person to come up with the idea, and he started his first transmission using DC. However, DC has so many issues when you are transmitting with DC. In order for it to go very far, you need very high current, and that's not effective. You do not want to have very high current, because when you have high current, the power increases exponentially. You remember what is P? P equals to I squared R, right? So,
Yes, sir.
so because of that, if your current is very high, the power loss becomes very high, So that's why DC is not something that we use for transmission. But however, at that time, Edison, he has the government in his pocket. He has the best research lab and what have you. So he lobbied and made sure the government was adopting his own power system. Then Tesla came from, I think, what's the name of his country? Poland, from Poland. And he joined the company of Westinghouse. I don't know if you know this guy. Also one of the popular entrepreneurs of that time. So the difference between Westinghouse and Edison is Edison, his researchers and his scientists, whenever they come up with an innovation or invention, he will patent it in his own name. So it serves as if he is the one who comes up with the invention. Okay. However, George Westinghouse, this is also another top guy. In his case, if you come up with your invention, he will ask you to use your own name to register the patent. So some of those brainiacs, they prefer to work for Westinghouse than to work for Edison. However, Edison has more money. He's the richer of the two. When Tesla came, the first person he met was Edison. And Tesla came with some idea of Tesla coil. They sat with Edison. Edison liked the idea. They had good vibe. And they tried to come up with a partnership agreement that will work. But Thomas Edison just decided to go around and play whatever he is used to playing. Almost, I would say, steal the idea from Tesla. So this broke the heart of Tesla. He got heartbroken. Before then, Westinghouse came to his rescue. He took him in and he gave him all that he needed to do his research. And that's when Tesla now come about AC. So when he brought AC into the picture, it was realized that, okay, now we don't have to be spending, losing a lot of power by transmitting DC, because AC can go very far with lower amount of current. So it's more effective. And some government officials started considering AC power. However, as I told you, Edison knows how to lobby. In fact, he started doing a massive campaign trying to tell people that AC is very dangerous, it can kill people. AC is very dangerous, it can kill people. So using that, they even try to associate AC with the power that goes into, I would say, that is used in execution rooms to execute, let's say, killers, okay? And they even do a video of one guy that was executed for death. They use AC to kill that person, and they use that for a massive campaign to tell people AC is a dangerous power. So because of that, that almost bankrupted Westinghouse, and that actually is one of the key things that even said made people believe Tesla lost his mind, because later on in life he became a bit crazy. So, but they have been fighting for almost 50 years. He has been fighting with Edison. But yeah, it's a very, very interesting story. For those who like stories, you can go and watch any YouTube video and you will see a more detailed story. So if you read all this, it's all about the news, okay? About what happens and but this one in a more formal way. Okay, so a transformer has two windings, okay? You will have what we call the primary winding, and you will have what we call the secondary winding. When you want to construct a transformer, normally you have two types of constructions you can use. We have the core form, and there is also the shell form. So for the core form, when you look at it, you will see that there will be a square like this, just a single square, okay, like this. And then you will come and you will make some windings, okay? You bring your current and you wind it up like, like this, bring it down, wind it, and you take it out. Same thing with here. So there will be no connection, okay? There will be no connection. Did I write? Okay, maybe yeah, something like this, okay? So these two windings will not be connected, and this is the core form. But for the shell form, it's like having ease. This one, I know you are, if you used to play, when we were kids, we used to open up transformers that are radio devices to just see what's going on inside. So you will see some metals like this, and in between them, you will see the coils wounded around. These coils also are not going to touch. We have these first ones, they are the primary, and the second ones, so these ones are the secondary. So this is how a typical transformer is constructed, either via the core form or the shell form. However, also in terms of the lamination of the transformer, we have what we call the laminated steel core. This is the most popular one that you normally see, and most students, this is the type they construct during their, their course project. Although some few that have the time, they can go ahead and construct this toroidal steel cores. Okay, these are the two types of lamination types that you come across when you are constructing a transformer. So now you know a little bit about this. Then the question is now, okay, is there any science behind it? How does it work? How many coils do I need? How many turns do I need, to have the transformer? If I want it to be giving me this amount of power, should I have 2 coils or 2 turns? This kind of science is what we are going to learn in the upcoming class, okay? However, transformers, in terms of when we put them in the power distribution system, they come in different types or different shapes. We have what we call the power, the unit transformers. We have what we call also the substation transformers, and we also have what we call the distribution transformers. These are the three types of power transformers you will see in the power station. So if you go to NEPA, I think they have a substation in BUK. If you go there, the transformers you will see are different from the one you will see outside electrical. So the one outside electrical is the distribution transformer, okay? If you go to that in the BUK powerhouse, you will see the substation transformer. And if you go to Dan Agundi, if you know Dan Agundi, that powerhouse where they are trying to make flyover. So if you go there maybe for a visit, you will be able to see a unit transformer there. Although unit transformers are mostly in the generation stations, because these ones, they are used to convert the generated voltages, power in the generation station. We want to step it up. So it will take it up to, let's say, 100 kilovolts and even higher for transmission. So this is the one that will come all the way, maybe from Shiroro Dam, Kaenji Dam, there from the turbines. So the transformer that steps it up is called a unit transformer. Then when it comes to the substation, we have a small one in BUK, but I think for Kano Metropolis, it's now Agundi. So if you go there, you will see the substation transformers there. It steps it down from that 110 kilovolts or higher to something in the ranges of 2.3 up to even 34 kilovolts. They come in different sizes. Then from there, it is taken and it will go all the way down to a distribution transformer, which is the 110 volts or 220 volts. The one you are using in your houses, okay? And also the one we are using in the department. So that's about transformers. Quick overview of transformers, the types of transformers, the construction. So keep this in mind. You might have to construct a transformer by the end of the course. All right. Now let's move to ideal transformer. And the question now, but any question before we move to the ideal transformer part? Okay, Abdullah Ali, you have question?
Hello, sir.
Yeah.
What's the difference between high frequency transformer with this type of transformer?
High frequency transformer.
Yes.
And which one?
And this
And
normal
which one?
transformer.
The normal transformer.
High frequency transformer and this normal transformer you are just showing now.
This why is this normal? You know, we have three. We mentioned three here, right? Unit transformer,
yes,
substation transformer, and distribution transformer.
Sure.
So which one are you referring to among these three?
I'm referring to there's one that is there is core inside it.
There is core inside it.
And core type.
All of them have this type of construction and coils.
Okay, sir.
Okay, I'm trying to understand your question.
I say there is one which is there is core which is black like a graphite or just a carbon.
Okay.
Is laminate the coil.
Okay. That's why the high frequency. I don't know. That's why I'm asking. I'm trying to also learn.
Okay. There is one which are using in small inverters.
Okay.
They are calling it high frequency inverter, high frequency transformer. Okay.
Now I'm understanding. Those ones are for devices, okay? They normally come in those smaller shapes. Okay. However, this one are called power transformers. Power transformers are mostly used for taking power from one destination to another. Okay. But keep something in mind. transformer, basically what it does is it takes voltage from one value, from one level to another level. Either it steps it down or it steps it up. Okay. And our power transformers mostly, they operate with frequencies around 50 Hz, as I said earlier, and 60 Hz if you are in the United States. However, high frequency transformers, those small ones, you know, they can operate at very high frequencies like 10 kilohertz or what have you. And they are, as I said, they are used in those electronic devices. Okay, they are compact. So they are mostly used for those small devices like inverter and what have you. But when you're looking at you know, substation transformers, these are very huge in size, very huge. Even the distribution transformers outside the department, I don't remember if it's still there, but I think it was there before. So even that one alone, if you look at the size, it's very huge. So they are different, they have different application. Okay, that's why this one we call them power transformers. Is that clear? Any other question? No question? All right.
No question.
So let's go and look at ideal transformers. So whenever you hear anything ideal, right, that's something that, of course, we cannot achieve in life, but that's an easy way of assuming perfect or perfection in life. So when something is ideal, we mean like if all things being equal, if we want to have a transformer, this is how we want it to behave. This is what we want from a transformer. So by studying an ideal transformer, it will give us an idea of how we can be able to analyze our practical realistic transformers. Okay? All right. So when you have an ideal transformer, normally when we are drawing, yeah.
What is the importance of ideal?
What the what?
What is the importance of ideal transformer?
Yeah, that's what I'm talking about, is to allow us to analyze and understand the working principles of a transformer. Okay, that's the main ideal. But if you go to the market to say, I want to buy ideal transformer, you'll never see it. It's not there, it doesn't exist. But it helps us, it like simplifies the whole analysis. When you try to do analysis with all the constraints in life, you know, taking all the impairments in reality, noise factor, losses, and what have you, so many things come into play. In communications, we have channels, okay? We have a channel we call AWGN. This is something that we use as an ideal, okay? Additive white Gaussian noise. It makes our life easy when we are trying to understand how a voice signal, right, moves from a transmitter like microphone up to a receiver, okay, where you are listening. So if I am calling you on your phone, scientists, in order to be able to design that phone or this thing that we are using to communicate, they assume that the channel is perfect. So ideal transformer is like a perfect transformer that has no issues. It has no losses. You know, that's what we meant by ideal. But it doesn't exist in real life. It just helps us to do some analysis to make life easy for us and get an understanding of the working principle of a transformer. Okay, is that clear?
Yes, sir. Yes, sir, I understand.
Okay, good. So we present or represent an ideal transformer in this form where we have like a cycle. Then, of course, you will have the primary windings and you will have the secondary windings. You will have current coming from the positive, going around the wind, and then coming out from the negative end. Same thing with the secondary. it is assumed that current comes from this and goes out through the positive. Okay, so you can see here the current is going in, and so on. Here the current is also going inside the flux. So I'm sure you remember Faraday and the right hand rules. We're going to look at them also, but yeah, when we come to motors or electromechanical machines. Okay, so this is one of the key formulas. You can just remember this. This is important. This we call it the turn ratio, where N is the number of turns, okay, in the primary, NP, in the secondary, NS. A is the ratio between NP and NS, and the voltage is also VP over VS is also equals to NP over NS. So if a transformer behaves in this way, where the voltage in the primary, the ratio between the voltage in the primary and the voltage in the secondary is equals to the ratio between the number of turns in the primary and the number of the number of turns in the secondary, you can call this an ideal transformer. Okay, you can call it an ideal transformer. And this is close, this ratio, we call it turn ratio. Okay, so what the relationship between the primary and secondary currents? Same thing, just that here is inversely proportional to the primary than in the case of the voltage. In phasor notation, we use VP over VS equals to A. IP over IS is also equals to 1 over A. So this is the characteristics of an ideal transformer. Is that clear? This is not big deal. It's not a big head-breaking calculation. It's something very easy to understand. And when we are dealing with ideal transformer and we would like to show where current is moving and how it is moving in a schematic way, okay, we use the dot. So if the voltage is positive at the dotted end of the primary winding, at some moment, the voltage at the secondary winding also will be positive at the same time. And in terms of power, you know this equation P equals to IV. However, since we are dealing with the AC, we have to always factor in the power factor, right? So that's where the cos P comes in. So P in the power that is going inside the transformer, because what part of the transformer is the primary, right? The primary side. So that's why the P in is the primary voltage times the primary current multiplied by the power factor in the primary side. Yeah. Yes? Somebody is asking? Okay. Same thing with the power out in the secondary. You can see P out equals to what? VS IS cos theta S. In ideal transformer, we assume that the transformer, because there are no losses, is a perfect system. The primary and the secondary power factors are equal. So we can replace this and this with just theta. No need to use pi. Okay, we assume to have the same power factor. So if that is the case, we can simplify our equations, okay, to say that P out equals to VS IS cos theta. But we also know VS from this simple equation here. We can do substitution, right? And we also know IS from this equation here, since we know A is equals to what? IS over IP, and A is also equals to VP over VS, okay? So we can just make substitution where P out is nothing but VPA IAP cos this. And if you do this, you realize that A and A will cancel each other. right? So you are left with VP IP cos theta. And this is nothing but what? Pn. So what are we saying is the power output or the power at the output of the transformer is the same thing with the power at the input of the transformer, meaning there is no loss. Our transformer doesn't have any loss, meaning the frame of the transformer is not losing anything. No power of ours is losing out, no leakage, nothing. If we are sending 10 watts, we are getting 10 watts at the output. Is that clear? This is a power transformer, and this is the real power, P. We also have the reactive power, which is Q, right? In the sign notation. So the Q out also would be equals to the Q in. Similarly, for the apparent power, S out and S in, these are also equal. All right. So this is the characteristics of a power or ideal power transformer. In the case of impedance transformation, what is that? And this is the last slide for today, okay? If you have an impedance it was like a resistor, but in the AC form, because now we are going to take into consideration L and C. So we use impedance as Z, okay? So Z, if you remember Ohm's law, right? R equals to what? VI, or you say V equals to what? IR, right? And so on. So that means R equals to what? V over I, right? And that's what we have here, V over I. So if you have a system or a circuit like this, where you have a load ZL, so the current that is passing through this load and the voltage across this load, okay, if we know them, we can just say ZL is equals to VL over IL. So if we know the load that we are putting on our system, and we know the voltage across our system or across our load, then we can be able to calculate the current. And this current at the output is nothing but the secondary current, IS. So that means IS and VS will be able to tell you your load voltage. However, there is something we do in transformer. Okay, and this is what we call the apparent impedance of the transformer, where now, you know, ZL, we are trying to look at it from the primary side perspective. We are not in the secondary. So we are assuming to make a transformation to look at it from the primary side. So assuming now ZL prime is equals to VP over IP. If you do also the mathematics, you can easily tell that if you know the load, okay, if you know the load in the secondary side and you know the turn ratio A, you can be able to tell what is going to be the impedance at the input or at the primary side. And this is called impedance matching. We want to do this matching to match the impedance in the primary with the impedance in the secondary. And with this, we have come to the end of the properties of a transformer. And then next week, we will just do the activity, okay? We'll just do the activity.
Yes,
I will
yes,
quickly
sir.
go over it, and we will do the activity and then start the next class, okay? So I have shared this lecture notes with you, and I would like you to not sleep on it. Just quickly brush it over. We are not going to have a quiz today because I still hear that some of you were having difficulties joining. So what we will do is the mobile app is going to be ready. The web app is ready, but I think some of you might not have power, and because of that, maybe your laptop will not be accessible. But since everybody is using a mobile device, even if you don't have, you can borrow from your friend. I will share the APK of the mobile app, okay? So that from next class, at least, even if you cannot or you are having technical challenges to join the session, taking the quiz will not be a problem, because then you can just use your mobile phone or your friend's mobile phone. Yeah, because I don't want to hear excuses that my laptop, no battery, no charge, no this, no that, you know. Okay. So another suggestion that was made by one of your colleagues is that maybe I can record the lecture for like 1 hour, send you guys the video. Then during the session, we will just focus on answering questions and then doing simulation, practice tests, and exercises. Yeah, that's something one of your colleagues mentioned, sent me an email to give this suggestion.
No, sir, it's not a good idea.
Not a good idea?
Yes.
Okay. So should we set a poll in the group?
Yes, sir.
Maybe, right?
Sir, it's a good. Sir.
Yes, sir.
I can see people are not happy. Many are saying not a good idea. Okay.
So instead of that,
Idea.
yeah, I'm thinking if you can use that, if you can like set up, even if it is once, a physical class, I think that would be better.
Yeah, we did physical classes. I am not in the country now. I think that's why we are doing all the classes online. Okay.
All right.
Yeah,
All right,
yeah.
sir.
So maybe when I return next week or upper week, we can have one session for more tutorials. But my main challenge with the physical class, I have to be honest, is because I use so many tools when I'm teaching. Okay. And unfortunately, in a physical class, I can't use those tools because of so many limitations. So my classes, physical, are sometimes, I will say, not that effective as I normally will prefer. And I've been perfecting my online lessons for almost 5 years now. Try to get everything in place because of the lack of infrastructure. So, but we will see. We will have maybe 1 or 2 physical classes when I return. But in the meantime, you have the recordings. I always share it with you. If you have any question too, you have my email. You can send your question via email, okay? With regards to the app and how to use it, please, I have been very busy, so I didn't get the chance to sit and make the video. I thought maybe during the class we will have time, but we are out of time. So I will still do my best to send the video over the weekend, okay, so that you can be able to do that. The assignment, I will share the assignment today. There will be no quiz, and the only assignment is the MATLAB assignment from yesterday. So I will share it today, okay? I will share it today or early in the morning, but I have it ready, so I can send it today. What else? Yeah, with regards to MATLAB, I haven't spoken to Dr. Amiru. I don't know if the class rep is here. So let me even send him a message right away. Please try to go and get it from him. Go and get it from him. Okay?
Okay, sir.
All right. Okay, so if you have no questions, yeah, I have yeah, somebody is saying since I'm recording, I can share the link. Yes, I do share the link after the session, right? So yeah, the main idea, I think, why that individual gave the advice is because he feels for those who couldn't attend, they can be able to watch the video of the recording or of the lecture before the session. They could be able to have some questions that they can be attended to during the session. I think that was one of the reasons why he gave that suggestion. But regardless, I think what we're going to do is we're going to see how we can keep improving. But recordings are there, and the app is going to help a lot. I will send the video of how to use the app. Please forgive me for the delay. I've been very busy and occupied. Okay, somebody is asking about the historical video. Yeah, You want to know about Tesla and Edison? There was a very nice video. I don't remember the channel, but I will look for it. Okay, I will share it in the group. Yeah, very interesting. Maybe 20 minutes. Is it Veritasium? Oh, I will check. I will check. I will send it, inshallah. I will send it. Okay. Anything else? Any question? If there is no question, then thank you all for being here. See you next week.
Thank you, sir.
Okay, bye. Somebody is asking, is exam going to be online? No, no, exam is not going to be online. Yo.
Online correct.
No. Exam is not going to be online. Only the quizzes, okay? Only quizzes, but exam, no. Exam is going to be on campus. Okay, bye.
Guys.